Cumberbatch to Sherlock Holmes, character identification TV series without a script. And it will be presented by Arsha Nagrani from Oxford University.
Thank you for the introduction. So just before I start, I'd just like to say a quick word about the title for those of you who are confused by the long names that I have. So in the recent adaptation of the TV series Sherlock Holmes, Benedict Cumberbatch is the actor who plays Sherlock, and I'll be using him as a running example throughout the presentation. So the goal of our work is, given a scene from a TV series or a feature film, and given some face detections to be able to identify every character in every frame of the video. So for this example, to be correctly able to identify John and Sherlock. And solving this task is useful for a number of different applications. Some of these could be, for example, intelligent fast forwards, so you can tell your system fast forward to when Sherlock first meets John, and it also brings us one step closer to the very difficult goal of understanding stories automatically from TV shows. So since 2006, most previous approaches to this task have relied on transcripts and subtitles as weak supervision, and this supervision tells us who is speaking when. But this supervision is only weak, and hence in practice, other algorithms such as multiple instance learning are also required on top of this, and most recent works since then have adopted a similar approach. So, however, in the last few years, CNN face descriptors have become extremely powerful. So the question that we investigate in this work is, can we recognize characters from TV shows without using transcripts and subtitles, and instead only using faces of their actors? And faces of the actors can be downloaded easily from the internet. And as it turns out, the answer to this question is no, we cannot. And the reason we cannot use only face descriptors, and the reason for this is that actors and characters actually belong to two different domains. So images of actors available from the internet are usually from red carpet photo shoots, and these are usually frontal, good lighting, standard expressions, they're usually smiling. But instances of characters in TV shows, on the other hand, cover a wide range of different poses, different lighting conditions, and can have many different expressions. And so going from Benedict Cumberbatch to Sherlock Holmes is actually not that straightforward. And this domain difference applies for all the other characters in the show as well. Besides this domain transfer, TV series and film material also come with a whole host of other challenges that standard CNN face descriptors trained on actor images cannot easily tackle, and some of these challenges include profiles, extreme poses, very dark scenes, small faces, and faces that are also partially hidden. So how do we deal with this? So three things are required to overcome these problems, and I'll describe each one briefly now. So the first thing that we do is we heavily augment the actor images, and we do this in three ways. We downsample the images first, and this helps us deal with low resolution small faces. We also reduce contrast, and this allows us to deal with the very dark scenes in the show, and as a standard augmentation practice, we also add horizontal fillers. The second thing that we do is we learn the face context of the character directly. So using augmentation alone, it is difficult to recreate different hairstyles, makeup, and expressions. I mean, we could do this, but instead we have a more straightforward solution where we train on images of the character directly. And the way we do this is we use extremely tight bounding boxes on the actor face, as you can see over here just above the eyebrows, and we train a face classifier on these tight props. We then apply this classifier to the character images and get a few instances of the character. Once we have this, we then extend our bounding box, so the region of support, to include the hairstyle and more of the face context. And we then retrain the classifier on this extended face region. So in this way, we can learn the hairstyle of the character, and also the makeup and other things, but not the hairstyle of the actor. And the final thing that we do is we incorporate the speech modality. So many approaches to this task have focused on faces, and they use the textual supervision from transcripts and subtitles, but very few have actually used the third modality available to us, and that's the voices of the characters. And for us humans, this can be quite a useful cue when you're watching a TV show, especially if different characters have different accents or different pitch. So the task then becomes that given an input stream, an audio stream, to say who the speaker is. And the way we approach this this task is by using a 4-stage pipeline, which I'll now describe. So the first thing that we do is we need labels for our voice segments, and since we already have our face classifier, we get the labels from the face tracks. The second thing is to get to know when a face track is speaking, so that we can get the audio segments, and we do this using active speaker verification. Now that we have our audio segments, we then extract voice features, and then using these features and the labels from stage 1, we then train a standard 1 versus rest SVM classifier. So I'll just briefly describe stage 2, 3, and 4 in more detail. So active speaker verification is done using a 2-stream CNN architecture called SyncNet, and you can read the paper for more details, but in essence what this does is it takes cropped images of the lips and the audio stream and determines if there is a correlation, that is the character speaking or not. So once we have the audio signals, we then extract features, and the way we do this is by converting the audio stream into a spectrogram. Since the spectrogram is essentially an image, we can now apply standard image classification networks. And I won't go into the details of our architecture too much, but the one thing that I will say is that we add an average pool layer, and the reason we do this is so that we can deal with variable length inputs. And we pre-train this network on an extremely large data set of speakers called Voxer. So now, finally, we have our voice features. We train a 1 versus rest SVM classifier, and we can then apply this classifier to audio segments where the corresponding face is difficult. So, for example, an extreme pose or extremely dark profile. And in this way, we get labels for these faces. So I'll now tell you how we put all these different solutions together into one system. The input to our system is actor images, and we can download these easily from the internet using the cast list of the TV show. We also have face tracks from the TV show, and we obtain these using tracking by detection. And the final output that we want from our system is a set of correct labels for these face tracks. So to do this, we use a semi-supervised approach consisting of 3 main stages. Each stage is a stronger face classifier, and the difference is that each classifier has a different training set with hard examples as we go on. So the first classifier is trained on images of the actor only, the second classifier is trained on character images, and the final classifier is trained on character images as well as harder face images, which we've obtained labels for from the voice modality. And a little bit more detail about how we do this. We take our actor images and train a classifier. We then apply the classifier to the face tracks and get labels. We then take the most confident labels and use those to create the training set for the second classifier, which is then trained on images of the character directly. We then once again take the most confident labels and use it to train the voice classifier, which is our separate speech modality. And using that, we can then add in some more difficult labels for the final classifier, and hence this will give us our best result at the end. So I'll show you a demo of the results at each stage. So I'll just pause to explain the key. So the first label that we have is the output of our first classifier, which is trained on actor images only. The second label is the output of the second classifier, which has been trained on images of the character as well. And the final label is the final output of our system, which includes the voice modality as well. So as you can see now, these are extremely easy examples. There's good lighting, they're mostly frontal, and so even the first classifier gets it right, but as you see later, we'll have some more difficult examples where you'll see some of the intermediate stages getting it wrong. So now the first stage gets it wrong at some points. So you can see we have some profiles which have been misclassified by the first classifier. Supposed to use sound for this?
Whether the echo goes on sound or not. Okay. It's not important. Not important.
So I think I'll just play that again.
Not important. Not important. It's okay. It's not important.
Anyway, so as you can see, this is quite a difficult example of Sherlock lying down, and so the first two face classifiers can't deal with this, but the final classifier that's been trained on labels after the voice modality gets it correct. So some more so we can look at the results at each stage again, and these are the results from the first actor classifier. Using the second classifier gives us significant improvements both in per character accuracy and overall, and the final classifier then gives us our best results. And just two things I want to point out over here. So for the character Mike, we actually had very few actor level images available online, and so you can see a big jump from inaccuracy from the first classifier to the second. And also for the character Mycroft, who had many speaking parts, you can see the big jump in accuracy from the second classifier to the third one, which includes the voice as well. So we can now take our approach as it is and apply it to completely different material. And so we choose the feature film Casablanca, which is a black and white film. And as you can see, the material is widely different, low quality since it's a very old film, and but our method still works, and we still correctly identify profiles, dark faces, and partial occlusions, and also, as you can see in the first frame, a large number of background characters. We also then compare our results to the state of the art, and we find that our method, which is the top one in yellow, beats all the previous works, even though these works have used the stronger supervision from transcripts and subtitles. So I'm going to show you the demo. Just want to check that the sound is on.
Mr. Art, I've been summoned. Coming? Here, if you want me to, of course. I'm lost without my blogger. You like the funny cases, don't you? The surprising ones. Obviously. Like this. The explosion.
Gassy, yes.
That was amazing.
Do you think it's possible?
Extraordinary, it was quite extraordinary.
So people who miss it, what English? Piss off.
So finally, to conclude, what have we missed? We've still missed some very small and dark faces. Also, extreme occlusion cases where we can barely see the face at all and the character isn't speaking. And back of heads, which we need to detect and then recognize, and this is something that will be the subject of future work. Thank you for your attention, and okay,
thank you very much. Time for one question. Yeah.
Where did you gather the voice training samples? Was it from the same movie or series, or?
Yeah, so it was from the same, the exact same show that we used, and it's part of the pipeline. So we get the training labels from our face tracks. So we have our face tracks. Once we know that they are speaking face tracks, we can then take the labels from in the second stage from our second face classifier. And then we then apply those labels and train the voice model. So so it's part of the entire process.
Okay, one more question.
In the last last demo that you showed, at some point actor 1 was talking and actor 2 was in the scene. How come that? So I think
Sorry,
it was,
in which part?
in the last demo,
Oh,
Sherlock was talking and I think John was on the screen while Sherlock was out of view. How come the third classifier picked John? Because it picks with the voice, right? So even if the two first classifiers said it John, how come the third one didn't get it?
So the final label was the final output of our entire system. So it wasn't just the label of the voice, it was the final output. And so this builds on the first classifier, the second classifier, and the third classifier. So that was the final label that I was showing. And so because the first classifier already got it correct, that then means that the final one was also right. So that label wasn't just the voice label, it was the final output of the classifier, of the entire system.
Okay, thank you very much.
Thank you.
Once again.